Welcome to your last video series of the semester. I know, I know, I get it, I get it, I understand. Cry it out, let it all out, because I know how sad you are and how sad I am. Okay, ready? Let's get going. Here we go. This week we're working on impulse and momentum. Impulse and momentum. We got 5 impulse momentum problems to go through. And we have some concepts prior to those, so let's dive in. Here we go. The old buddy, F is equal to ma. We all know the most important equation in all of first semester, if not all of physics, period. Okay, we won't discuss that today, but just trust me, it is. So here we have F is equal to ma. Let's do something nifty and or cool with this equation. Let's take the acceleration, which we all know is a change in velocity over change in time. So, okay, that's acceleration, all right, plug that in, and we get F is equal to m, change in velocity over time. It's FMA, it is, it's just a little different looking. I just substituted out the A with delta V over T. Now, because this is America, doggone it, and we can do this if we want to, let's take this T and move it to this side. So let's multiply both sides by t. So get rid of t here and put t over here. Okay, why would you want to do that? Well, because 1, I wanted to in America, and 2, check this out. So now we have FMA. This is FMA, just substituted and arranged a little bit. FMA. And we have 2 sides of the equation that we need to focus on for this week. This side of the equation, force times time. That's called impulse. 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 Okay, all right. So that side, force times time, is called an impulse. Then this side of the equation, we have m, mass times multiplied by velocity. In this case, I put a change in velocity. But I can actually take this delta and move it out to the front of the m, because if I change either the velocity or the mass, I'm going to change this side of the equation, which we call momentum. M times V is momentum. And momentum, a word you've heard of before, something you know about. You do. You know that a freight train moving at 60 miles per hour would have a butt ton of momentum. You would know that a mosquito moving at 60 miles an hour would not, because you know that the mass of something has something to do with momentum, and it's got to be moving. I mean, if I have this marker and it's not moving, it has no momentum. It's got mass, but it's got no momentum. So those combinations, that combination of momentum, mass and velocity gives me my momentum. And you knew that. You did. You knew. Okay, so I'm going to take this and just put my delta out in front, meaning if I change my mass of an object, then I'm going to change its momentum. Or if I change the velocity of an object, I'll change its momentum. So here I have my 2 equations. This is mom, call it mom for short. And momentum it actually has a letter that goes with it. It's a Greek letter, row, row, row your boat gently down the stream. And that row is also, sometimes you'll see it just as a P in our alphabet, P. And that is equal to mass times velocity. Mass times velocity. I got a visitor. Woo! And that mass times velocity gives me momentum. And so that is this part of the equation. All right, so that is the 2 parts of the equation that we need. I'm exhausted. Whew, had to run all the way. It's exhausting. Where was I? Oh yeah. So this, if we look at the units, that F is a Newton, and that time is a second. So the units on the left are Newton seconds. The units on the right are going to be mass, which is kilograms, and velocity, which is meters per second. Those are equal to each other. There's a little unit analysis here. those units have got to be the same because on both sides of the equation they're equal. So this is Newton seconds, kilogram meters per second. Don't believe me? Do a unit analysis for your lonesome. This would be kilogram meters per second squared multiplied by seconds. Seconds cancel. Boom, you get that. Okay, so there's our unit analysis. Now, a lot of times in physics, we take a couple of units and we give them a special name. Not in this case. Both of these are just what they are. Those are your units for momentum and impulse. All right. We are going to use this equation a couple of times. And one thing we want to, actually before we dive into the math of using that equation, let's go over a couple of concepts that are important for this equation. If I look at this, you know that there's something true about this that you just don't know that you know, but you know. Okay, here's what I'm talking about. Okay, if you're Tiger Woods, Tiger Woods, getting ready to hit that golf ball. Get all, you know, watch those golfers, they go these little weird things, and before they settle into their shot, settle. Okay, here we go. I want to hit this ball as far as possible. What do I have to do? Do I just stop, or do I follow through? You know the answer to that. You have Tom Brady. No, we don't want to talk about him. Yeah, too sad. Okay, let's say that Joe Schmo quarterback wants to throw a football as far as possible. What do? Do they stop there? Or do they follow through? They follow through. You want something to go as fast and as far as possible. As far as possible, it has to go fast. You know that from projectiles. The faster something goes forward, the farther it's going to go. And the way you get something to go fast is you apply a force for a long period of time. There it is. Impulse is equal to the amount of force you apply for a certain amount of time. If you apply a force for a longer period of time, then you'll get the object, the mass, to have a larger change in velocity, which means it'll go farther. So you see, this is about force being applied for a certain period of time. If I apply a force just for a little time, then it can, okay, it's not going to change very much. But if I apply a force for a long period of time, I'll get a velocity change, get that thing going really fast, make its momentum even greater. So, big impulse change, big momentum change. All right, we know that. Here's something else we know. This impulse equals change of momentum has to do with safety devices. Safety devices, what are we talking about? Like padding below a gymnast who might fall on the floor. Padding, okay? Helping them not get injured. Or an automobile where you've got an airbag, or you have a safety belt. That has to do directly with this equation right here. Let me give you an example. Or boxing gloves is another one. Without boxing gloves, you know, Newton's third law, I hit you, you hit me, break hand. Boxing gloves, we don't break hand. Fight goes longer, more entertainment. Let's go to automobile. Let's say you're traveling down the road at 20 meters per second. It's a little bit more than 40 miles per hour. And you hit a tree. Okay, that's gonna be a bad day for you. Tree wins. Trees just win. They're trees. You hit that tree, you are going to stop in one way or another in a very short amount of time. Hopefully you've got a seatbelt on, otherwise you're going. But let's say that you didn't have your seatbelt on and you went and hit the steering column or go through the window and hit the tree yourself or whatever. When you do hit something solid, you're going to stop very quickly. Let's do some math here. Let's say that you are a person of 100 kilograms. And you're moving at 20 meters per second. Okay. You are going to come to a stop. So your change in velocity, my change in velocity, so actually with this problem, this momentum change is due to the change in velocity. I'm going 20 meters per second, I end up going 0, I will stop. So when I have my change, I put it from 20 to 0 is 20. Over here, you stop very quickly. I'll just make a number up. Maybe you stop in a tenth of a second. Okay, it could be a little longer than that, a little shorter than that, but like 1/10 of a second. 0.1 seconds. How much force would be applied to this person's body? We can solve for that. How much force would be applied to this person's body? Do the math. 100 times 20 is 2,000. Still with me? Divide by 0.1. Okay, divide both sides by 0.1, that'll give me the force applied to this person. That's around 20,000 newtons. Now, if you remember G-forces at all, you take the mass, or you take the weight of the person, you divide the weight of this person into that force. Okay, the force applied to the force they normally feel, which would be their weight, to how many G-forces this person would be subjected to. That's going to be over 20 Gs. This person's weight would be 980 newtons. 980 goes in there over 20 times. 20 Gs is a really bad day for you. Really bad day. Probably dead. Especially depending on what part of your body you're hitting. Head first, boom, dead. Yeah, you'd probably dead. Okay. Maybe not instantaneous. Maybe you hit a lot of internal bleeding, still dead. Bad day. Now, here's what I wanted to show you though. What if you had an airbag? Was there an airbag in front of you? You should have your seatbelt on too, but let's just say you have an airbag, and that decreases the time to stopping from 0.1 second to maybe 0.8 seconds. So less than a second. Well, actually, let's just make it a second. I'll make the math a lot easier. Let's say you stop in 1 second. You're not stopping in 1/10 of a second, which is like the tree. You hitting the tree and go, you stop in, because you got that cushy airbag. You stop in 1 second. Makes the math easy. You see what's going to happen. That becomes 1 second. That becomes 1 second. This becomes 2,000 newtons, which should be just a little bit more than 2 Gs. It'd be more than 2 Gs, which we couldn't survive that. We laugh at that. Silly. Well, maybe not laugh at it, but you're going to survive that. Okay, so the point is, we are using impulse and momentum to solve a basic problem of safety. So the physics reason that airbags work, the seatbelts were the same thing. They increase the amount of time that you stop. It's not an instantaneous stop, or nearly instantaneous. Nothing can be instant, but close to instant. That you increase this value of time, you decrease the force applied. When this one goes up, time goes up, force goes down. Same thing with boxing gloves. You have padding there. And that padding, when you hit somebody with those boxing gloves, that padding increases the amount of time that the force is being applied. Then increase of time, decrease of force. Okay? All right. That's our introduction to impulse and momentum. And from there, we will now pick up the problem solving.